Hey everyone, 3.14 pi. Well, not really, because it's 3.1.4, but close enough. Defining rigid transformations. Throughout American history, quilters have used transformations to create intricate geometric designs. For example, the quilt at the right is an example of design based on rotation and reflection, while the quilt at the left contains translations, rotations, and reflections. In Lesson 313, you found ways to locate the image of a shape after it is reflected. Today, you'll work with your team to develop ways to describe the image of a shape after it's rotated or translated. Rotations on a grid. Consider what you know about rotation, a motion that turns a shape about a point. Does it make any difference if a rotation is clockwise versus counterclockwise? And we've talked about this before. Absolutely. What ends up happening is a totally different location if you rotate something 90 degrees clockwise versus counterclockwise. And are there any situations in which situations does it matter? 90 degrees, it matters. Anything other than 360 or 180. So at 360, you get right back to where you started. No harm, no foul if you went clockwise or counterclockwise. Anything 360 or 180 doesn't matter. And it could be a multiple of those as well. So if you did 2 full rotations and got right back to the start, like a 720, it also wouldn't matter if you went clockwise or counterclockwise. Are there any circumstances in which it does not matter? Sorry, kind of answered that one. But yes, the 180 and 360. All right. The other things we could talk about would be like really specific situations. Any situations where it does matter. If you were trying to unlock a lock on a locker and you went the wrong direction, it wouldn't work. Like if you were supposed to go clockwise and you went counterclockwise or vice versa, it wouldn't work. The lock wouldn't open. And circumstances where it does not matter, if you've ever had a salt grinder or a pepper grinder, it doesn't matter if you go clockwise or counterclockwise, you will still get salt. Now, mind you, on my salt grinder, if I go clockwise versus counterclockwise, one direction gives larger pieces of salt and the other direction gives smaller pieces of salt, but both directions will provide salt. And are there any situations in which the rotated image lies directly on the original shape, and that is only at 360? Investigate these questions as you rotate the polygons below about the given point. Use tracing paper if needed. So you can use tracing paper or wax paper in order to do these, but I'm going to do them out sort of the traditional way because the wax paper is really easy to do yourself. 180 degrees. If I want to rotate this 180 degrees, you know that there's one little dot there for the center of rotation. It doesn't help much to have just the center of rotation if you're going to do this sort of the traditional way. What you need to do is put in the axes. So I would personally draw in an x-axis and a y-axis to make this easier for myself. So if I'm going to go one up and I want to go 180 degree rotation, instead of going one up, I'm going to go one down. Instead of going one up and one left, I'm going to go one down and one right. Instead of going 1, 2, 3 up and one left, I'm going to go 1, 2, 3 down and one right. Instead of going 1, 2, 3 up, 1, 2, 3 left, I'm going to go 1, 2, 3 down, 1, 2, 3 right. Up 1, 1, 2, 3, 4 to the left would be down 1, 1, 2, 3, 4 to the left. And then there's a point diagonal from that. And you would get a 180 degree rotation. That's really tricky to do if you don't draw in a set of axes for yourself. Now, that one said 180 degrees, and you'll notice that they wanted us to go clockwise, so this one came to here. What's going to happen if you do 180 counterclockwise? You're going to end up in the same place. It's just you're going to turn that way, and you're going to get the exact same shape in the same location, even if you went clockwise versus counterclockwise. And that was just trying to prove the point from above that 180 doesn't matter clockwise versus counterclockwise. So the next one that's here, again, it's really important that you draw in that set of axes for yourself so you know where you're going. So this one is a 90 degree and it is clockwise. So whatever's here is going to end up down in quadrant 4. So this one is right 1, up 1, 2, 3. So I'm going to turn my paper and go right 1, up 1, 2, 3. And then I'm going to go back. And I'm just going to go straight 1, 2, 3, 4 up. So if I rotate my paper, 1, 2, 3, 4, up. And then the last one is left 1, up 3. And so this one I'm going to go left 1, up 1, 2, 3. And then I have one that is directly 1 point to the left. And this would be the equivalent of 1 point to the left. And so you can see that I ended up with a 90-degree rotation from things that were in quadrant 1 ended up in quadrant 4. Now this is the same shape, but this one wants 90 degrees counterclockwise. So again, we have to predict where are we going to end up. So if we're going to go 90 degrees counterclockwise, this is going to go down here. So the point that was on the x-axis, the point that was on the y-axis is now going to end up down on the x-axis. So right 1, up 1, 2, 3. Notice I'm going to rotate my paper in the other direction this time. And I'm going to go right 1, up 1, 2, 3. Or I can go straight up 4. Or I can go the left 1, up 3, turn my paper, left 1, up 3, and then we had the point that was directly left 1. So that is rotating 90 degrees in a counterclockwise. All right, next, we've got 270 degrees, and this one is asking us to go clockwise. Remember that 270 clockwise is the same as 90 degrees in the other direction. So the 90 degrees in the other direction would be the same as this one. Whoa, where am I going? 90 degrees. Oh, I drew that in the wrong way. Yep. We got to go this way this time because the first one was clockwise. So my 90 degrees is counterclockwise, which would be the same as the one that we just did. And we would end up 1 point down, 3 points up. I'm just replicating the one that's here because 90 degrees counterclockwise is the same as 270 clockwise. So that one's going to be up 1, over 1, up 1. There we go. I didn't draw in the axes this time just because I was replicating a previous one. 360 degrees. It is going to end up in the exact same place. It's going to end up on top of each other because 360, whether you go clockwise or you go counterclockwise, you're going to end up exactly where you started. The letter N, you will notice that it is symmetrical, that this one is pointing down on the left and this one is pointing up on the right. So if you do a 180-degree rotation, this one ends up down here, this one ends up back up here, and you would get the same design as you started with. And last, the square. The square has rotational symmetry every 90 degrees. That should sound familiar from MSM 3. So if I rotate 90 degrees, this corner ends up on this corner. This corner ends up on the next corner, and so on. The only way I would have to do anything to this drawing is if it had letters, if it had vertices. The vertice labels would have to change. But because both of these have rotational symmetry, it would also end up in the same spot. Now, this one has rotational symmetry every 180 degrees, so it ends up directly on top of itself. Upside down and right side up look the same. This one has rotational symmetry every 90 degrees because it has 4 sides that are identical. And if you divide 360 by 4, you get that it has rotational symmetry every 90 degrees, whereas the letter N shape has rotational symmetry every 180 because it's only divided by 2. All right, so the next page, definition of rotation. So what exactly is a rotation? If a figure is rotated, how can you describe it? On graph paper to the right, graph the points 4, 1, and 2, 5. 4, 1, and 2, 5. All right. Then use tracing paper to rotate the 2 points 90 degrees counterclockwise about the point 0, 0. Mark points A prime and B prime on the graph paper. So this was A, and in order to get here, I went right 4, up 1. So in order to get a 90-degree counterclockwise rotation, right 4, up 1, I would have to do the same thing for it to end up in quadrant 2, right 4, up 1. And that one would be A prime. B, in order to get there, we went right 2, up 5. So in order to get to B prime, we would go right 2 and up 5. Again, I want to point, sorry about that, quite off the screen. Right 2, up 5. Want to point out that I rotated my paper because I predicted where it was going to go. 90 degrees counterclockwise, anything from quadrant 1 is going to end up in quadrant 2 for 90 degrees counterclockwise. Draw line segments that connect A to O and B to O. All right, so I can do that. So I'm going to use a ruler for this. You could sketch it by hand. It's not a very long segment. So A to O, and then I'll switch and do different color, B to O. All right. And then also A prime to O and B prime to O. So A prime, I'll use the red color so you can see that I create an angle with the two red segments that happens to be 90 degrees because we rotated 90 degrees. And then the blue segment also rotated 90 degrees from B to B prime. Compare the lengths. So if we wanted to measure how long the red segment was, the red segment here, about 7/8 of an inch. And I would say the same on the A prime O, also about 7/8 of an inch. We said rotation was a rigid transformation. It shouldn't get longer or shorter. Which lengths are equal? So we would say that length AO is congruent to A prime O. And we would also say that BO is congruent to B prime O, that the red lengths are the same as each other and the blue lengths are the same as each other. Which angle measures are equal? Angle AOA prime, that's the red angle, is congruent to angle BOB prime, which is the blue angle. To help, you may want to draw line segments, and that's what we have here to show those angles. Predict the measure of angle AOA prime. And so what do we say? AOA prime, the red angle, is 90 degrees. And we can verify that. Now, you can use a protractor. If you don't have a protractor handy because we're looking at 90 degrees, you can take something that has a corner that's a right angle and you can slide it in there and you can see that the red segments actually make a right angle. You can do the same thing with the blue segments. You can slide it right in there to see that the blue segments also make a right angle. Why does it make sense for all points P on the graph, a rotation about a point O, that it moves to a new point P prime so that OP is equal to OP prime? So what they're saying is, why does it make sense? Why is OP always going to be an equal length to OP prime? And why is the measure of POP prime going to be the angle of rotation? We said that rotation preserves the distance and all of the points get rotated the same amount. This is talking specifically about rigid transformations. So rotation preserves distance and all of the points get rotated the same amount. You can use tracing paper as well to check this, a ruler and a protractor, or in this case, I used a Post-it notepad. They would all work to check for that 90-degree angle. Use tracing paper to help you examine why a rotation does not change any angles or preserves lengths of a figure when measures do not change. Some mathematicians use the term preserved. The angle measures are preserved. If you go back to the front, this would be a good one to use tracing paper on just to show that the original figure stays the same size and the same shape as the image. It's also great for being able to show your rotational symmetry for the N and for the square. Definition of reflection. So now we've really defined and talked about rotations. So let's go back to reflection, which we did earlier. Now that you know more about the slopes of parallel and perpendicular lines, revisit the reflection from problem 325 and confirm the relationships you found. Use the diagram at the right, which shows PQR reflected across line L to form P prime, Q prime, R prime. Use your ruler and draw 3 dashed line segments connecting the corresponding points. What's the relationship between the dashed segments? So if I connect P to P prime, you will notice that they make that dashed line makes a 90-degree angle with a line of reflection. If I connect Q to Q prime, which is supposed to be dashed, but it really only got one dash, is also a 90-degree angle with the dashed segments and the line of reflection. And the same thing from R to R prime, which I remembered to dash, 90-degree angle. So use your knowledge of slope to verify. So one thing that we said was that it makes that 90-degree angle. We can also check slopes. And this is a really cool connection to the last section. If we measure P to P prime and you look at like how much you go down and how much you go over, Q is going to be a better one. So if I go from Q to Q prime, and I go down 2, right? 1, 2, 3, 4. The slope is -2/4 is -1/2. That's the slope of the dashed line. So if I color code this, this has a slope of -1/2. And this line of reflection, if you pick a couple good points, has a slope of 2/1, which is positive. So we said in the previous section about parallel and perpendicular lines, if they are perpendicular, you would have the same slope. So all 3 of the dashed lines have the same slope. So the dashed are all parallel. They're all a slope of -1/2, but perpendicular are opposite reciprocals. Run into my slope there. Now focus only on segment RR prime. What is the relationship between the line of reflection and the segment RR prime? We just proved, because their slopes are opposite reciprocals, that they are perpendicular. Use slope to confirm the line of reflection is perpendicular to the line RR prime. And yes, one is -1/2 versus the one next to it, which was a positive 2/1. Place a point N at the intersection of RR prime and the line of reflection. What do you notice about the lengths? So they're saying if you were to put a point right here, how long is it from the line of reflection to R versus how long is it from the line of reflection to R prime? And those two segments would be congruent. Same length from the left side as it is the right side. Is what you observe for segment RR prime true for any segment connecting a point with its image? That is the line segment connecting a point to its image always perpendicular to the line of reflection? Well, we've proved for this example that all 3 of the dashed lines are in fact at a 90-degree angle to the line of reflection. And is the line of reflection always a midpoint? So is this segment on the left always equal to this segment on the right? Is this segment on the left always equal to this segment on the right? And is this segment on the left equal to this segment on the right? They're not all equal to each other, but the left versus the right have to be equal. And the answer to both of these would be yes. Now, this is the first half of the notes, and I'm just going to cut the video off at this point. So if you need to take a break, you can. Totally understand that. And then pick up part 2 when you're ready.